Good morning, everyone. Welcome to the 8th lecture in the NMR course that you have been going through for the past couple of weeks. In yesterday's lecture, we ended up writing the rate of change of magnetization mx, my, mz as the Bloch matrix, which was minus r2 minus capital omega, omega 1 sine phi, capital omega minus r2 minus omega 1 cos phi and minus omega 1 sine phi, omega 1 cos phi minus r1 times mx, my, mz plus 0, 0, r1 m naught. This is what we refer to as the Bloch equations or the Bloch matrix, which helped you deduce the time evolution of magnetization based on the various relaxation parameters R2, which is spin spindle relaxation, R1, which is spin lattice relaxation, the offset that's associated with the difference in the frequency of omega naught of the given spin to the omega r of the transmitter frequency. The phi is the phase angle subtended by the BRF with respect to the x-axis of the rotating frame, and omega 1 was given by minus gamma b1, where b1 is the amplitude of the BRF that is being applied. What we did was to see the application of the above equation to a 90-degree pulse. If I remember correctly, in the class I did a 90-degree x-phase pulse starting from equilibrium, which is 0, 0 m naught, and we were able to understand this would result in 0 minus m naught 0, indicating that a 90-degree x-phase pulse would end up changing m naught along z to m naught minus m naught along y-axis. Alternatively, one could also say it is m naught along minus y-axis. Let me try to draw that vector picture of the same. From here on, I lose the indices of the rotating frame. We have m naught, which is a bulk magnetization, and we were talking about a BRF that's applied along the x phase. Sorry, I made a mistake here. B1 that's applied along the x phase on resonance. What would it end up doing? It would end up tilting m naught from z axis to m naught along minus y axis. It's basically a right-handed coordinate frame where a counterclockwise rotation ends up happening with resulting in m naught along the minus y axis. This is what we had ended up seeing. And we also were able to understand if non-equilibrium state exists, how does longitudinal magnetization recovers? Similarly, we also saw the equation how transverse magnetization decays. These were the two things that we saw. And the whole idea behind this was that if you ended up applying a rectangular B1 pulse and then you recorded a signal, and the name of the signal is called the free induction decay. What's free about it? free precession that happens following the application of pulse with respect to B naught, the induction that is a result of the magnetization M naught precessing about B naught that cuts a coil and therefore results in a magnetic induction, the decay of the transverse magnetization that results in loss of signal over a period of time. So the first thing I would like to do from here on is to write a general way of looking at the magnetization as a function of time. It's going to be given by m naught times sine alpha cos omega t exp minus r2t. If you might remember, we did not write this previously, but now we are writing a general term for mx of t following application of alpha degree pulse. In this case, it's the y-axis based pulse that is applied with an offset of capital omega. Previously, we saw an on-resonance condition where, if you might remember the curve, it was just decaying as a function of time. The moment you have an offset, the cos capital omega t term also comes up. Pretty sure you guys remember how e power minus r2t comes. This is nothing but dmx over dt equal to minus r2mx. That results in this part of the term. So this is the signal that comes up following alpha degree pulse that's applied along a y-axis. Similarly, the functional form of the my magnetization is going to be m naught sine alpha sine omega t exp minus r2t. What this means is that since you have an offset, that offset will result in the magnetization in the transverse plane that is going to precess not at its Larmor frequency, but in the difference of the frequency offset, which is omega naught minus omega RF. You're already at omega RF. Now you're assuming there is a non-zero offset, which means that the omega naught is different from omega RF. Remember, this could be positive or negative. And that will result in a precession about B naught. This is going to be a precession frequency that's definitely less than 500 megahertz. If you're assuming the 500 megahertz, it's going to be in the range of kilohertz. Recollect the example of ethanol that we saw, where we said if CH3, CH2OH, if you end up setting this as the offset, we said OH will be at say plus 1000 hertz and CH3 will be at minus 2000 hertz because of the chemical shift difference of the methyl, methylene and the hydroxyl protons. This is what we started the entire lecture with. So this indicates that the offset that you have is going to be different for different spins except for the one that's on resonance. What we saw in the previous lecture was all on resonance. Therefore, any deviation that comes from on resonance case, you're going to see an oscillation. This is exactly what we had seen in the simulations as well, just that the simulation assumed the omega equal to 0. But I'm sure if you guys are able to understand, if you slowly make sure the omega RF is not equal to omega naught, you're going to see a difference that comes up. Of course, I'm not trying to say the omega naught is different for these protons. There's something called a shielding parameter, which will end up changing the Larmor precession frequency slightly based on the electronic environment, which is what we will see hopefully at the end of this lecture. So what we have done so far is to see how the representation of the magnetization goes. But interestingly, this is not what we end up measuring in reality. We'll measure something like m plus of t, which is mx plus my. This is very similar to the ladder up, ladder down operator that you might have studied, or even the angular momentum operators that you might have been exposed to in quantum mechanics. This is the example of the angular momentum operator from the rigid rotor model. So similarly, the magnetization in the transverse plane, which is denoted as m plus, is given as mx plus my. If you're asking why a plus sign is given here, one might imagine this as the two energy levels that are being present. And if you might remember, this is the plus half state, this is the minus half state. You are making a transition, if you call it difference in quantum level, is going to be half minus of minus half. Basically, transitions that happen from alpha to beta to alpha is going to be plus or minus 1. So it's a single quantum transition that starts to come up. So therefore, the plus 1 indicates a single quantum coherence that's generated. I'm sure you guys might recollect from the previous lecture, what does coherence mean? We are talking about a phase coherence that exists. Therefore, m plus of t, the signal is going to look as m naught sine alpha, which is constant, times cos omega t plus I sine omega t times exp minus r2t. The m naught sine alpha part is constant for both mx and my. If you might remember the previous equation, let me show it in a moment. We're able to realize the m naught sine alpha e power minus r2t part is common for mx and my. Therefore, if you end up adding mx plus I my, you have I part here, which will make it cos omega t plus I sine omega t. With that being the case, you end up getting this, which can now be minimized into m naught sine alpha exp I omega t exp minus r2t. This functional form of the free induction decay is very important to understand how an NMR signal starts to come up. The important aspects of this is that this is the strength of bulk magnetization. Alpha is the flip angle that is applied. Exp I omega t, we'll come to this in a moment. This is actually an oscillation. Why do we call it an oscillation? You have cos omega t and I sine omega t. We had seen this earlier. When you have omega as the angle between x and y axis, the x projection is going to be cos omega t and the y projection will be sine omega t. And as the omega keeps changing, it basically keeps going around in circles. So basically it's an oscillation. Oscillation meaning it has a certain frequency associated with it. The last part here is the relaxation part, meaning since you have generated a non-equilibrium state following application of a 90-degree Y phase pulse, it has to relax back to equilibrium. That's given by the minus R2T term. Here we are only looking at the transverse magnetization, so you have only the minus R2T term that exists. As you are able to realize, we wanted to determine frequencies, not time domain data. And how do we end up getting it? The signal in the frequency domain is obtained from signal in the time domain. I'm trying to write the capital S for signal in the frequency domain, small s as the signal in the time domain. Basically, the FID we are trying to measure. If you have the time domain information, you could end up applying something called Fourier transformation, which ends up relating inversely related variables. Basically, frequency and time are inversely related. Therefore, the frequency information is contained within the time domain signal. Therefore, you can extract all of that from the time domain signal. So how does one write the Fourier transformation? The Fourier transformation of capital S of omega is given by 0 to infinity S plus of t times exp minus I omega t dt. This is basically the definition of Fourier transformation, where this is called the integrand Depending upon the various types of transformation, this part will keep changing. You could have a wavelet transformation, you could have a Lorentz-Gauss transformation. There are different types of transformations that one could do. The S plus of t is signal, where the S plus of t is directly proportional to the m plus of t, which we had written a moment earlier. So basically, it all connects back to the fact that if you know the functional dependence of m plus of t, you know the functional dependence of s plus of t, then if you end up applying the magical Fourier transformation, you will get the frequency domain spectrum. If you end up applying this, the signal would end up coming in two parts. Remember one thing, here this part of the integral has a complex term associated with it. So it's not a simple Fourier transformation, it's a complex Fourier transformation. Complex meaning you have real and imaginary parts that are being present. Why would we want it? Because our signal also has real and imaginary parts. We'll also slowly try to understand why both parts are essential in NMR spectroscopy. So in order to do this, let's carry forward. So basically, the signal S of W will come up as V of omega plus I U of omega, where if you do a complex Fourier transformation, you're going to get a real part and a complex part, where the complex part functional dependence is going to be given by V of omega. V of omega is proportional to m naught times R2 the whole divided by R2 square plus capital omega minus omega the whole square. What is the small omega here? It is the running variable. We will see when we plot this, how does it look. U of omega is also proportional to m naught, but in the numerator, it's going to have capital omega minus omega R2 square, capital omega minus small omega the whole square. So let me copy and write this again. Basically, we have a time domain signal that we end up measuring as S plus of t. And this S plus of t, if you end up doing a Fourier transformation, you get capital S of omega, which is the frequency domain spectrum. This frequency domain spectrum has a chemical shift, scalar couplings and all that. But to make things look simpler, you have two terms, a real term and an imaginary term when you do this complex Fourier transformation. And importantly, these two terms have their own set of names that go with it. This term is called the absorptive part, and this term is called the dispersive part. Let's try to take a look at what do they mean. If you try to plot let us say V of omega, it will end up coming like an NMR Lorentzian, meaning as a function of small omega, as the small omega keeps approaching capital omega, the resonance intensity keeps increasing. You're able to realize as this becomes smaller and smaller, denominator becomes smaller and smaller, and there is a position at which the maximum that you're going to get is 1 over R2. Basically, it's proportional to that. I'm not saying it's equal to that. You'll have R2 over R2 square. That will make it as the 1 over R2 term that's being present. Of course, as you start moving higher and higher, the magnitude increases. That means the denominator starts to increase and the signal starts to die. The most important aspect of this is that the half line width, which you would be able to calculate, if this part is proportional to m naught times 1 over R2, one can actually calculate what is the full width at half maxima. What is that going to be? M naught times m naught times 1 over 2 R2 on either side of it. Which side of it? This is the resonance that you wanted to see at a given offset, and these are the values as they start going away. And remember, every spectroscopy is associated with a line shape. This line shape is called a Lorentzian line shape, and the full width at half maxima can be calculated using the dependence that is shown here. Therefore, you would be able to determine, if you know this is the maximum intensity, determine the value of omega where you have the intensity as listed here. In which case, you would be able to determine what is the full width at half maxima. This will be one of the exercises I suggest you guys to do. Moving on, what is that we wanted to see here? We wanted to see how does the dispersive part also look. So that is the exercise I would be doing right now. Let me choose the color orange for the dispersive part. The dispersive part, on the other hand, has a capital omega minus omega in the numerator divided by R2 square plus capital omega minus small omega the whole square. So therefore, as the omega keeps increasing, especially when omega equal to capital omega, this goes to 0, this also goes to 0. So therefore, you're going to have no signal while omega matches capital omega. So you are able to realize at the resonance, things are going to cross, and especially for values where small omega is less than capital omega, you're going to have a positive term on the numerator. And for values of omega greater than capital omega, you're going to have a negative term. So if you end up plotting this entire curve, you would end up getting something of this sort. This is why it's called the dispersive component of the resonance. And this is dispersive and does not die that easily, largely because it has a 1 over omega dependence. On the other hand, the absorptive part has a 1 over omega square dependence, rather 1 over omega minus omega square dependence. That means it dies very fast for values of small omega that keeps increasing. On the other hand, for the dispersive part, it just depends on 1 over capital omega minus omega, therefore it doesn't die that easily, meaning that the resolution is better. For absorptive line shapes. So NMR, we generally get signals in the absorptive form. If you guys might recollect, in an EPR spectrum, people end up doing the first derivative in order to find where is the frequency, because it has a very large plateau where one cannot figure out given a noise. On the other hand, NMR has a Lorentzian line shape where there is only a single point in which a maximum happens. Therefore, the absorptive line shape itself is enough to give you what is the resonance frequency, which is what you wanted to find as capital omega. So why are we doing this? Because we said we wanted to measure capital omega, which has all the information of chemical shift and scalar coupling. So that's where we are. Let's try to spend a little bit of time on how Fourier transformation ends up helping. By no means I'm trying to say I'm giving a comprehensive definition of how Fourier transform works. But for the purposes of this course, I'm going to show you some functional dependence on how things look, and therefore hopefully will impress upon the point on how FT helps, Fourier transformation helps in NMR spectroscopy. Cos omega t, when one ends up Fourier transforming, I'm going to put that as a double-headed arrow, will result in a signal which is delta of omega plus delta of minus omega, meaning that, we try to draw it here. Let's say this is a time domain signal and the frequency of this is capital omega. If you end up doing a Fourier transformation, you will get a frequency domain spectrum where you're going to get two lines, one at plus omega, another at minus omega. Basically, the cos function, when Fourier transformed, cannot distinguish whether the frequency is positive or negative. It gives a signal in both the places. If you end up just substituting cos of capital omega t here and do the integration, you will understand how this functional form ends up coming. Similarly, if you end up taking the sine component of capital omega t, when you end up doing a Fourier transformation, I actually trivialized a few things here, but it's okay. I think this is enough for the understanding right now. This is going to be delta at plus omega minus delta at minus omega. So basically, you had a plus sign here, which resulted in the phase of both the Dirac delta functions that look like that. Now, how is this signal going to look? Let's draw it. Sine function starts with 0 and keeps oscillating. And that's going to result in a frequency domain spectrum. Here as well, you're going to get a signal plus omega and minus omega. The only difference being the signal in plus omega is positive, the signal in minus omega will be negative. So what you are able to see is that if you want to get the true frequency, which is the offset plus omega, you cannot just use a sine component or the cos component. You got to use a combination of both these components to get it, where if you end up doing a complex Fourier transformation, the plus omega part, which is the true signal part, gets added up and the minus omega part gets cancelled with each other. So which is why if you end up doing a complex Fourier transformation, just writing CFT as a way of looking at it, what are you going to get? You won't get a signal at the carrier. You will only get a signal at plus omega. So this is what is called quadrature detection. What is quadrature detection? You just cannot measure the x component or the y component. You need both x and y component, which is why instead of measuring mx or my, we end up measuring m plus. You can also, on the other hand, measure m minus, where m minus is nothing but mx minus imy. So having said this, this is why we kind of realize that we need the m plus signal, which has the e power I capital omega t, which will help you distinguish the resonance aspect. Now the immediate question comes up, if Fourier transformation of e power I omega t is just a delta function, why does the width come up? Why does the width come up? You should have had a resonance which looks like a single line at the carrier frequency, which is how I have drawn it here. So this comes up because Fourier transformation of exp minus r2t results in the Lorentzian line shape. So basically you will end up getting r2 over r2 square plus omega minus omega square. This is what is the Lorentzian line shape. Basically the relaxation parameter gets embedded into it. Basically if you have a decay that's happening, it will result in a Lorentzian line shape. So therefore a combination of Dirac delta function. Let me try to draw the time domain and frequency domain components of each. You're going to have decay that's being present. This is what we called as the e power minus r2t. And therefore, this one is going to give at 0, this is going to end up giving you a Lorentzian line shape. So what are you able to understand from this? exp I omega t when Fourier transformed gives you a Dirac delta function at capital omega. Because it has a combination of cos part and the sine part, therefore you end up getting this. Let's also draw this to make our point nice and easier. Okay, one has to be careful here. The cos part will look like this. And the sine component will be opposite of phase with respect to so this is the sine part, while the red one is the cos part, which when you complex Fourier transform, you will end up getting a signal only in the plus omega. Why do we get only in the plus omega? Meaning, this is the Dirac delta function, this is the Lorentzian, and when you end up convoluting, what is convolution? End up taking this shape and sweep it across this shape. So what will end up happening? You will end up getting the free induction decay. I'm only going to draw the cos part just for the sake of clarity. How will that look? This is the cos omega t exp minus r2t. In all of these plots, the x-axis is time. So you're able to see the signal decays and the oscillation remains, which has the omega component associated with it. I'm sure you guys will be able to translate the green one that goes opposite in phase but keeps losing signal as a function of time, which when you Fourier transform will result in a signal that is convoluted wherever the signals are. Basically, you get zero everywhere. This is the absorptive signal that we are referring to. So I hope this has served a little bit of understanding on how this signal, which we ended up measuring as evolution of magnetization in the time domain, which is called the free induction decay, ends up converting itself into frequency domain spectrum. So let's go back and take a look at this. So this is entirely a signal. I'm rating only the cos part. The sine part also exists. I'll write that explicitly. Plus I sine omega t exp exp minus r2t will result in a Dirac delta function convolution with a Lorentzian to get a peak maximum at your omega. So this way, what is going to happen if your omega is plus 1000 Hertz with respect to the carrier, you're going to get a peak there. Your omega for the methyl group is minus 2000 Hertz with respect to the carrier, you're going to get there. And for an on resonance one for the methylene, you're going to get one such. So therefore, I hope I've been able to convince you that the CH3, CH2, OH molecule for which we set the carrier at CH2 part of the molecule, where this is at plus 1000 Hertz. As I said, these are approximate numbers. This is at minus 2000 Hertz. Why do we do this? Because you remember we had this kind of a spectrum that you ended up getting CH3, CH2, OH. How did it start coming up that way? Your spins that end up having their own M naught, and due to the chemical environment being different for each one of them, they have a slightly different Larmor precession frequency. The precession frequency is the same, but there's something called shielding, deshielding that happens that results in different frequencies with respect to the methylene group. And when you end up measuring the free induction decay, Each of them have their own omega associated with them, and each of them have their own R2 term. So the R2 for methyl group, the R2 for methylene group, R2 for hydroxyl group, all will be different. So will be R1 for each one of them. R1 for methyl, R1 for methylene, and R1 for OH are all different from one another. They need not be the same. So all put together would result in a free induction decay that is a sum of all these signals. Okay, so basically the overall free induction decay is a linear sum of free induction decay of methyl plus free induction decay of methylene plus free induction decay of the hydroxyl proton. The moment you get each of the free induction decay, you are able to understand that we end up applying Fourier transformation, complex Fourier transformation, which will result in overall frequency domain spectrum, which is a frequency domain spectrum of methyl plus frequency domain spectrum of methylene plus frequency domain spectrum of the hydroxyl proton, which now results back in a spectrum that looks like that. Yeah, so each of this FID will have its own, let me write it for example, each of this will have its own M naught of methyl times exp. Let's assume it's a 90-degree pulse that's applied. I omega of me times t exp minus R2 of me times t. Similarly, for the methylene, it's going to be the magnetization of methylene product e power I omega of methylene times t times exp minus R2 of methylene times t. Similarly, you will be able to realize this will also have its own M naught, its own omega of OH, and then its own R2. Since NMR is a linear technique, each of these FIDs which add together in the time domain results in an entire spectrum, which is nothing but a summation of each of their signals that are being present. I hope this lecture has been useful in trying to understand from the from the Bloch equation how a general functional form can be shown for the mx and my components of the magnetization following a 90-degree pulse or an alpha degree pulse with respect to an offset. And with that being said, how is the signal being measured in the transverse plane? You don't have to keep it along x or y. You keep it somewhere there. You end up measuring m plus or even m minus. And m plus indicates a single quantum coherence, so does m minus. And this coherence that's being measured is called the free induction decay, which when Fourier transformed will give you the frequency domain signal, and the relationship of the Fourier transformation is given here. And the signal that you end up measuring in the time domain is enough to get the spectrum in the frequency domain. This spectrum, the frequency domain, has two components, an absorptive component and a dispersive component, both of which have the same information of capital omega and R2 for spins that you're looking for. However, since the absorptive part decays as 1 over capital omega minus omega square, it's a very sharp resonance. On the other hand, since this is 1 over capital omega minus omega, this ends up having a broader decay, resulting in the fact that we prefer to get absorptive lines. But remember one thing, the full width at half maxima will be decided by the dispersive component in these parts, and the same should match. Although I'm not drawn it in a nice way, these will end up matching with each one of them. Okay, so with that being the case, we did not end up studying Fourier transformation. We just said that if you have a cosine function, if you end up doing Fourier transformation, you get a Dirac delta function, irrespective of whether it's plus omega or minus omega. But if you end up doing the same Fourier transformation of the sine function, you get similar information of both peaks at plus and minus omega, just that they are opposite in sign with respect to each other, which when you end up adding put together of cos part and the sine part, you get signal only in the cap plus omega part, which is where your signal originated from. This is rather easy to understand because oscillations of cos of minus omega or plus omega cannot be distinguished because cos of theta is equal to cos of minus theta. So basically that's what it's trying to say. A cos function cannot distinguish between the plus component or the minus component because of this relationship. On the other hand, while the sign can distinguish them, the relative phase is just opposite to one another. You can always face things where this is opposite and you never be able to find what is the right answer. Therefore, you just cannot measure cos part or the sine part to get information. You need to measure the cos part and the sine part, which when put together will give you a necessary Dirac delta function at the frequency that you want to look for. Now, how does the Lorentzian end up coming? The relaxation component results in the Lorentzian, which when convoluted with the Dirac delta function will give you a Lorentzian at the resonance frequency. So this overall sums up how an NMR signal ends up coming up from the magnetization that was generated due to the quantum magnets that are present. I'm sure there are quite a bit of questions that are there. I will discuss with you in the next class. So please be prepared. In this regard, I request you to read the equivalent parts of the Kavanagh book, the Once Pulse experiment, so that this becomes a little more easier while we discuss. Thank you very much and good luck.